Welcome to the AICE Chemistry lecture series. Today we're going to look at chapter 5, section 4, which covers the solid state of matter. Now, for the solid state of matter, you have to realize that most compounds, when they're solid, are going to have some form of lattice. So we're going to be listening to that word a lot. Most ionic, metallic, and covalent compounds, regardless of what type of compound it is, when they're in the solid state, form a crystal lattice. A lattice is essentially just a regularly repeating arrangement of ions, atoms, or molecules in 3 dimensions, meaning it's something with a pattern. A lattice is an arrangement for a solid compound that is going to give the either ions, molecules, or atoms a regular pattern that they follow. The difference between the lattices of different types of compounds is not how they're arranged, although that can vary even within the same compound, but the type of particles that are arranged within the lattice. So we're going to look at all types of compounds in this unit, anything from ionic compounds to metallic elements to covalent molecular compounds, which is what we are used to seeing. And we are going to look at a new type of solid or a new type of compound called a giant covalent network. We're going to start by looking at one that we've talked about multiple times in the past, both in honors chemistry and in AS. Ionic lattices, or the ionic compounds, form lattices that have ions at the vertices of the lattice. Now, what is the vertices of the lattice? If we imagine a lattice like this, where we have alternating positive and negative ions for an ionic compound, the vertices are simply just the locations where we found those particles. In the case of an ionic lattice, the vertices are going to either contain a negative ion like chloride or a positive ion like sodium plus. Now, depending on the size and the arrangement of the ions, there are different ionic lattices that may form, and that's something that you might see if you ever take a college inorganic chemistry course. But for AS chemistry, we focus on the most basic of these lattices, which is just a cubic lattice, which is shown here. A cubic lattice is the most common form of the lattice, which just has a repeating arrangement of positive and negative ions, with the ions having 6 other ions of the opposite type surrounding them. So if we focus on this sodium ion here in the center, the Na plus ion, you can see that we have a chloride ion above it, below it, a chloride ion to either side of it, and a chloride ion in front and behind it. This is what is typical of an ionic cubic lattice, where we have an ion surrounded by 6 other ions of the opposite type. And this is true as well of those negative ions. So if we look at the chloride here, we have 1, 2, 3, 4, 5 sodium ions that we can see, but you have to remember that this drawing gets repeated over and over again in any direction. It is a giant lattice. It is something that repeats over and over and over again. So if we were to put another copy of the lattice of these squares on this side, we'll have another sodium ion on this side where the key is. So we'll have 1, 2, 3, 4, 5, and the one we're not seeing, 6 on the right side. So that's one of the key features of these lattices, that we can actually repeat them over and over and over again. If we grab one little cube, we can put another cube on the right, then another one below it, another one above it, so on and so forth, and they keep repeating over and over and over again. Compounds with 1-to-1 ratios, like sodium chloride and magnesium oxide, where the ratio is 1-to-1 and the size of the ions is very similar, form these cubic ionic lattices. Regardless of the type of ionic lattice, though, whether it's cubic or some of the other ones that you might learn in a college inorganic chemistry course, these ionic compounds are always going to form this type of ionic lattice, where at the vertices of the lattice, we either have positive or negative ions in this repeating pattern. And that repeating pattern is why this is a lattice. Now, the ionic lattice gives the ionic compounds some specific properties. Now, this lattice and the structure of solids is what gives a lot of these compounds their properties, and you need to, for the AS exam, be able to talk about and describe what the properties of a special type of compound is and why they happen. Now, this is something that we see a lot in questions, in explanation questions on paper 2. And the first step, like we talked earlier in this chapter, is always going to be to try to decide what type of compound are you looking at. Is it ionic? Is it covalent? Or is it a metal? And so when we look at ionic compounds are going to have specific properties. For example, they're hard. They have a specific hardness where if you put pressure on them, they won't buckle. And that's very simply because ionic compounds have really strong ionic bonds. So that's the first part of this. The bonding type, it can provide certain properties. Because ionic compounds have very strong ionic bonds, they are hard because the ionic bonds prevent them from breaking apart when only pressure is put on them. Those strong ionic bonds are what's holding the lattice together, and it's very difficult to move or scratch those crystals. On the other hand, ionic compounds are also brittle, and this is something that might seem like a contradiction to you, saying that an ionic compound is brittle and hard, but they actually address two different things. Brittleness is how something responds to getting hit, to a sudden, really strong force. Whereas hardness is how something responds to constant pressure. Ionic compounds are hard. If you ever have put your hand down on a bunch of salt crystals, you know it hurts. However, they're very brittle. A large crystal of an ionic compound is brittle because ionic compounds have charged ions in their vertices. They have alternating charged ions. And the problem with having alternating charged ions is that if a row of ions is moved, then they end up next to a row of like charged ions, causing repulsion, which breaks the crystal. So let's look at this in a drawing. So let me change over here. Imagine we have the ionic compound or lattice we talked about before. Let's say sodium chloride. We have Na plus ions alternating with chloride ions. So I'm going to put here Na plus, Na plus. And I'm just going to draw 3 rows of these. So then we have the Na plus ions, and then alternating with those Na plus ions, we have chloride ions, Cl minus, Cl minus, Cl minus. Now, in this structure, and I drew this two-dimensionally for the sake of simplicity. In this structure, we have negative ions next to positive ions. This attraction between the negative and the positive is what we call the ionic bond. And because we have negative and positive ions next to each other, they're all going to attract each other and hold the crystal in its lattice form. However, what happens if I come in with a hammer and with the hammer or something very strong, I suddenly hit, not put pressure on, but put a lot of force into this lattice? What's going to end up happening is that the lattice will shift. So in this case, I'm going to draw my first column is going to be very similar to what I have, and the second column too. But the third column of the lattice, because of that sudden force, is going to shift. So I'm going to put the chlorine here, chloride ion, chloride ion. So what happens is when I hit this crystal, this whole layer shifts down because of the sudden force. When that layer shifts down, now I still have in parts of this crystal those ionic bonds where the positive and negatives were not shifted. However, now I have positives next to each other and negatives next to each other. What's going to happen is that these are going to repel each other, forcing this whole layer to be shifted away from the main body of the crystal. What that creates is a break in our lattice that causes our crystal to break. This is why ionic compounds are brittle, because the sudden force can shift layers and have positive ions and negative ions next to each other, causing repulsion instead of the attraction that normally keeps the compound together, and therefore it causes the crystal to break. And that's what where the brittleness of ionic compounds comes from. So again, they're hard because of the strong bonds, but they're brittle because if we give it a sudden force or hits with a sudden force, the like charges end up next to each other and the crystal ends up breaking. Moving forward, we also have another property of ionic compounds, which is that they have very high melting and boiling points. And the very high melting and boiling points, just like the hardness, comes from the same place. Ionic compounds are held together by strong ionic bonds. Strong ionic bonds, and this is very important to say, require a lot of energy to break. This is why the melting point and the boiling point of ionic compounds is high, because it requires a lot of energy to break those bonds. And so it requires a really high temperature to break those bonds and create the liquid or gas state for an ionic compound. The bigger the attraction between the ions, the higher the melting and boiling point of the compounds is, and we talked about this in chapter 4. Remember that there are two things that are going to affect the strength of the ionic bonds, and that's going to be when we have a higher ion charge. So the higher the ion charge, the stronger the ionic bond, and smaller ions. Remember, smaller ions means stronger ionic bonds. So ionic compounds with higher ion charge and smaller ionic bonds are going to have a higher melting and boiling point because their strong ionic bonds take a lot more energy to break. Now, that's not to say that ionic compounds with low ion charge and large ionic radii are going to have low melting points. They're still going to have high melting points because we still have strong ionic bonds, but they're going to have lower melting and boiling points than an ionic compound with a higher ion charge and a smaller ionic radius. So you need to be able to compare those things. Compare the ion charges on the ionic radius of different ionic compounds to compare the melting and boiling points based on the strength of the ionic bond. Next. So solubility, and this is something that we've talked about in the past in honors chemistry, and we're going to keep talking about as we go through AICE chemistry. Solubility. Most ionic compounds, not all, but most, are soluble in water. Ionic compounds are usually soluble in water because of ion dipole forces that they can form with water. Ion dipole forces are the force of attraction created between an ionic compound and the polar water molecules that surround the ions when that compound is dissolved. So, let's look at that again with a diagram. So imagine we have the same compound that we're just working with. We'll keep going with sodium chloride. Sodium chloride, NaCl, is very soluble in water, like most ionic compounds. If we have solid sodium chloride and we dissolve it in water, so we're going to put aqueous here. Remember, aqueous means a lot of water. So if we have NaCl solid plus aqueous, we're going to get aqueous sodium chloride. But if you remember from our conversation from last year, any ionic compound that is soluble, when it's aqueous, will separate into its ions. So realistically speaking, to put this into a net ionic equation, sodium chloride solid, when exposed to water when dissolved, will create separated sodium ions, aqueous, and chloride ions, aqueous. So let's look at that at the atomic or molecular level, or in this case the ionic level. If we have the lattice, and I'm going to draw the same lattice I drew before, so Na plus, Na plus, Na plus. So we have the sodium chloride lattice. In the sodium chloride lattice, at the vertices, we have sodium ions, which are positive, surrounded by chloride ions, which are negative, and vice versa. So this is the sodium chloride lattice. Whenever that sodium chloride lattice is added to a large amount of water, which we usually represent by saying aqueous instead of H2O, because H2O will mean that they're reacting with the water, what happens is that those sodium and chloride ions separate from each other and are no longer in the lattice format. And that's because of the water itself. Water molecules, which I'm going to draw here in red. This is big. So water molecules, I'm going to draw one here by itself, have an oxygen and a hydrogen. And those water molecules have polarity. They're polar molecules. We talked about this already this year and the last year. The oxygen is partially negative and the hydrogens are partially positive. So because of the polarity of water, water is going to be attracted to both the negative and positive ions. With the positive ions, the water molecules are going to be attracted to that sodium ion, which is positive, with the oxygen pointing towards the sodium. Why? Because the oxygen is partially negative and the sodium is partially positive. So they attract each other. That attraction that they form between the partially negative oxygen and the positive sodium ion is what we call an ion dipole force. Because it's the force of attraction between a pole on a polar molecule like water and an ion of an ionic compound. So what ends up happening is because of those ion dipole forces, the sodium ions in a sodium chloride, when it already dissolves, are going to be surrounded by water molecules with the negative waters, or partially negative waters, pointing towards the sodium ion. This process of surrounding the sodium, the ion, is called solvation. So solvation, not salvation, solvation, is the process of water molecules forming ion dipole forces and surrounding the ionic compound, or the ionic ion, from the ionic compound that's being dissolved. Not to be confused with dissociation, which is the process of an ionic compound separating into its individual ions. These processes are related. Dissociation happens because of solvation. So the dissociation of sodium chloride to sodium ions and chloride ions happens because the water molecules undergo solvation of the ion due to the ion dipole forces that they create. With the chloride, the exact same thing happens, but the water gets arranged in the opposite direction. With the chloride, the positive hydrogen ions, or the positive hydrogen in the water, are attracted to the negative chloride ions. So when the water is drawn for the solvation layer of the chloride, we put either like this or like this, the hydrogens from the water facing the chloride ion. And that's because the chloride ion is an anion. It is negatively charged, and the water has a partially positive hydrogen, which is attracted to the negative chloride. Now, that ion dipole force is still created here between the hydrogens and the chloride ion. And that's what keeps this solvation. This is still solvation, it's just solvation of a negative ion instead of a positive one. And so the water molecules are drawn the opposite way. This process of solvation and dissociation, along with the forces created during the process, which are the ion dipole forces, are the reason why most ionic compounds, when exposed to water, dissolve, why they're mostly soluble, because they dissociate into their individual ions. Now, this is how you explain, going back to what we were doing, this is how we explain that all ionic or most ionic compounds are soluble in water, due to the ion dipole forces form and the process of solvation. Finally, ionic compounds are electrically conductive when molten or dissolved. Whenever an ionic compound dissolves or is melted, that ionic compound can now conduct electricity. In the solid state, ionic compounds do not conduct electricity. They're locked into the lattice and can conduct electricity. But when they're melted or dissolved, we get ions that are mobile and then can conduct electricity. This is one of the biggest things that you have to remember about electrical conductivity. There is one thing that is needed for something to conduct electricity, and that is the presence of a mobile charged particle. In order for something to conduct electricity, it needs to have a mobile charged particle. Now, mobile means that it's moving, that it can move around. Charged particle means that it can have a charge. So ions are charged particles, electrons are charged particles. So with ionic compounds, they conduct electricity when melted because they have ions, which are charged particles, that are mobile. But in the solid state, even though they do have ions, which are charged particles, those ions are locked into place in the lattice and therefore are not mobile. So they, in the solid state, they check off one of the requirement, a charged particle, but not the other, which is a mobile charged particle. In the liquid or aqueous state, however, they check off both of these. They have mobile charged particles, and so they can conduct electricity. And that's the easiest way to explain electrical conductivity, is that we need a charged particle that is mobile, and in melted or dissolved ionic compounds, that will be those ions that are free to move around. But in the solid state, they're locked into place in the lattice, and so they are not mobile, and therefore cannot conduct electricity. So these are the general properties of an ionic compound, and those are the explanations that you will give on the AICE exam if you're asked why they happen. Ionic compounds are hard because of the strong ionic bonds holding them together, holding the lattice together. They're brittle because even though they have strong ionic bonds, because the ions, when shifted, you end up with like charged ions next to each other, they repel each other and they break. They have high melting points and boiling points because of the strong ionic bonds that are holding them together. And again, that's going to be further made stronger by any higher charge ion and smaller ionic radii. So you need to be able to explain the melting points and boiling points of ionic compounds and say that they have strong ionic bonds holding them together. But you also need to be able to compare ionic compounds to each other and how their melting points and boiling points will compare based on the charge of the ion and the size of the ion. The more highly charged the ion is and the smaller the ion is, the higher the melting point because the stronger the ionic bonds. They're all soluble because of the ion dipole forces created between water and the ionic ions in the ionic compound. So the process of solvation and dissociation is what makes most ionic compounds soluble. And finally, they're electrically conductive when melted or dissolved because they have ions that are mobile and able to move around, but they're not electrically conductive when solid because those ions are locked into place in the lattice and therefore are not mobile. Those are your explanations. So let's move on to metals. Metallic lattices. Metallic lattices refers to the structure of a metal. And we actually talked about this at length in honors chemistry. Metallic lattices are metals that are pure or mixed together to form alloys. So a metal forms a metallic lattice because whenever the atoms of a metal come together, their electrons are removed and ions, metallic positive ions, are created. When metallic atoms give up their electrons, they form cations, and those electrons are released to become delocalized. Now, this is an important word that you need to learn. We can no longer use the term sea of electrons that we used in honors chemistry. We now use the term delocalized electrons. And all that means is that they don't belong to any one atom. They're free to move around. Delocalized electrons are going to flow between the cations of the metal all over the lattice. And so they look like this. We have the metal cations with those ions, electrons flowing in between them in the delocalized electron area. And this is something that we saw in chapter 4 when we were discussing metallic bonding. Now, the one thing I do want to remind you from chapter 4 is that to remember that these metallic ions in the metallic lattice and the electrons have a specific ratio. So let's go and draw a structure again. If we have something like, if we're comparing the sodium metal, so sodium solid versus aluminum, Al solid, we have to be very conscientious about how we draw these. So the general shape of the lattice will be the same. For sodium, or for aluminum, we're going to have metal cations. So let's draw sodium, Na+. So metal cations, because sodium's ion is +1. So Na+, Na+. And those metal cations are going to have the electrons in between them dissolved. And pardon my drawings. So for sodium, when we draw these electrons, we are going to draw these electrons in a 1-to-1 ratio. Why? When sodium turns into an ion, sodium Na+ turns into an ion, sodium solid, when it turns into an ion, will turn into a +1 ion, releasing 1 electron. Meaning that the sodium ion and the electrons are in a 1-to-1 ratio. So when we draw the structure of a sodium metal, we need to be careful that if we draw 6 sodium cations, we draw 6 electrons. If we draw 7 sodium cations, we draw 7 electrons, because it's a 1-to-1 ratio. With aluminum, on the other hand, when aluminum creates its lattice, it forms a 3+ ion. That's a common ion of aluminum, aluminum 3+. So when I go and draw the aluminum lattice, well, first of all, I'm going to draw Al3+ to make it known that I know the charge of the ion. Don't just draw like this plus, because we are talking about a specific example of metallic bonding. And so when aluminum forms its ion and creates the 3+ ion, it creates a 3+ ion by releasing 3 electrons. So now we have a 1-to-3 ratio between the cation and the electrons. So when we draw an aluminum lattice, we need to make sure that we draw 3 times more cations than, or 3 times more electrons than we're drawing cations. So if we have 1, 2, 3, 4, 5, 6 cations, we need to draw 18 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So it doesn't matter where we draw them because they're delocalized, they're flowing around. But we need to make sure that we draw 18 electrons because we need to draw 3 times more electrons than we do aluminum ions because of that 1-to-3 ratio. Now, what is actually the metallic bond and the metallic lattice? Both of these are the metallic lattice. The structure of metallic lattice is the cations with the delocalized electrons in between them. And that's what creates a metallic bonding, which is the attraction for these cations to the delocalized electrons, regardless of how many there are. The only thing that's going to change from one metal to another is the ratio between the cations and the delocalized electrons. But the metallic bonding is also stronger with more electrons. So if we have a higher charge ion, we are going to get a stronger metallic bond because there are more negative charges and a higher positive charge. Now, the other thing that will affect this, that doesn't here because these are in the same group, or in the same period, should I say, but the other thing that will affect this is ion size as well. So metallic bonding strength is affected by the exact same thing we just discussed with ionic bonding, which are the size of the ions and the charge of the ions in the metal. So, going back. So let's discuss the properties of metallic compounds then. Metallic properties and structure. The metallic properties are going to follow the same logic as the ionic ones. Now, they're obviously different, but the logic that we use for them is the same. So how do we look at metallic bonding and the properties of a metal, like their melting point, boiling point, malleability, ductility, and all that? Well, malleability and ductility are what we're going to discuss first. If you remember from honors chemistry, malleability and ductility are two properties of a metal that deal with their ability to be shaped. With malleability, it is the ability to be pounded into thin sheets, and with ductility is the ability to be drawn into thin wires. Now, both with malleability and ductility, we are looking at the shaping of the metal, right? Whether it's something that we're pounding down into a flat sheet. Oh, thin, not thin. So whether it's something that we're pounding into a flat sheet or a thin, or something that we're drawing into a thin wire, we're talking about shaping the metal. Now, why are we able to shape metals but not ionic compounds? Because as we saw earlier, ionic compounds are brittle. They break when we hit them with force. Whereas a metal will deform or create a new shape. This is because of the sea of electrons in a metal lattice. The sea of electrons act like a buffer, and because they're mobile, because they can move around and reform, they allow the lattice to keep its shape without repulsion. Because when I hit a metal, the sea of electrons or the delocalized electrons will keep their shape around the deformity, keeping those cations away from each other. So, if we look at our structures like we had earlier, let me erase some of this so I can work. If I look at my aluminum, for example, if I look at my aluminum and I hit the aluminum with a hammer, just like I did with my ionic compound earlier, what's going to happen is if I grab a hammer and I hit the aluminum lattice, instead of the cations getting too close together and repelling, like happened with the ionic lattice, what's going to happen is that the cation will shift, but the localized electrons will shift with it. So if the aluminum ends up here, instead of where its original location was, the localized electrons will shift with it to prevent the cations from touching each other and repelling. So that force of attraction between the cations and the electrons are still there because the electrons shift and take up the space of the new location of the cation. And because of that, instead of breaking, the metal lattice can actually adapt to new shapes. And so it gives the properties of malleability and ductility to those metals. Next is the high melting point, high boiling points. And this is exactly the same as it was for ionic compounds, only instead of the attraction between the anions and cations, it is the attraction between the metallic cations and the sea of electrons. So the strong metallic bonds holding the metals together are omnidirectional, and they take a lot of energy to break, just like with ionic compounds. And so they have very high melting points and boiling points. The bigger the attraction between the cations and the localized electrons, the higher the melting point is going to be, and the boiling point is going to be, just like with ionic compounds. The only difference was that instead of the localized electrons, you had cations and anions. But that means the same thing. It means that if you have a higher cation charge or a smaller metallic radius, you're going to get stronger metallic bonds that take more energy to break and therefore higher melting and boiling points. Finally is the electrical and heat conductivity of the metals. Metals, unlike ionic compounds, are always electrically conductive and they always conduct heat, meaning that it doesn't matter whether solid, liquid, gases, they're always going to conduct heat. And that's because of the same rule that we had before. Remember that what is necessary for electrical conductivity is mobile charged particles. So what are the mobile charged particles here? The mobile charged particles are the delocalized electrons. The delocalized electrons, The delocalized electrons in a metal are mobile, they can move around, and they're charged particles because electrons have a negative charge. And so they can conduct electricity and heat very well. Metals can conduct electricity and heat in any state because of the delocalized electrons being able to move around and either carry energy for heat or carry electricity, which is just a flow of electrons, for electrical conductivity. So again, because of those mobile charged particles, in this case the electrons, we have both heat and electrical conductivity for the metals. Now, like I said, metals can either be a singular metal, like aluminum, sodium, gold, silver, or they can be a mixture of metals. Now, with a mixture of metals, we get what we call an alloy. So let's look at that now. Alloys and their properties. So when a metal does not have the properties we require, we create what is called an alloy to make a metal that has the properties we want. An alloy is a mixture of two or more metals or a metal with a non-metal. Now, what makes this different from an ionic compound? Because if you see the word metal with non-metal, right, that usually implies to us that we have an ionic compound. But the key here is that we can mix either multiple metals or a metal with a non-metal, but it is not a compound because there is no bonding. It is a mixture. A physical mixture of one or more metals, or a physical mixture of a metal with a non-metal. That's what an alloy is. That's what differentiates an alloy for something like an ionic compound, which has a specific ratio of metal to non-metal. And there are no ionic compounds that have multiple metals. We can create two different kinds of alloys by working with the metallic lattice: an interstitial alloy or a substitutional alloy. With an interstitial alloy, we are usually going to add a non-metal usually, but it could be a metal. But the key thing here is that they need to be sufficiently small that instead of disrupting the metallic lattice, they're going to fill the spaces between the metal ions. So interstitial alloys are ionic lattices that we have added something that is small enough that instead of taking the place of one of the metal cations, they're simply going to fit in between them. A very clear example of an interstitial alloy is steel, where carbon is added to iron and it takes the spots in between the iron cations. So that's an interstitial alloy. It is an alloy where the thing that we're adding, what we call the doping agent, the thing we're adding to the metal, is small enough that it fills in the spots between the metal cations in the lattice instead of replacing the metal ions. On the other hand, a substitutional alloy is the exact opposite. A substitutional alloy is usually made between metals, although there are exceptions, but the doping metal ion is big enough that it will substitute the original metal in the lattice. Brass is an example of this. So instead of the doping agent, whatever we have added, being small enough that it fits in between the lattices, it instead takes the place of the metal cation. So we get this pattern where we still have our metal lattice, but instead of all the cations being of the same metal, we have different metals in the lattice. So maybe these are, I think in the case of brass, if I remember correctly, it is copper and zinc. So maybe these are copper that were the original metal, and the zinc cations have replaced some of those copper cations. So this is 2 plus. So the copper, which was the original lattice, had zinc added to it, and the zinc cations in red took the place of some of those copper cations in the lattice, and that's what makes a substitutional alloy, because it is being substituted into those into the lattice. Whereas an interstitial alloy, like this one, let's put this here, iron 3 plus, has the doping agent, in the case of steel, which is that being carbon, fitting in between the ions of the metal in the lattice instead of taking their place. So that's the main difference, or the only difference, between an interstitial and a substitutional alloy. So let's look at some specific examples of this. Some specific examples that you might want to learn about, or that are in your curriculum that you have to learn about for interstitial and substitutional alloys, are things like brass. Brass is an alloy that's made of 70% copper and 30% zinc. Brass was made because brass is stronger than copper, because the zinc in the brass replaces some of the copper ions in the lattice. So brass is a substitutional alloy. Since zinc is a slightly larger metallic radius, it prevents the copper from sliding past itself, making it stronger. So that's what this picture right here is. So let me see if I can zoom in on that. No, let's go back. So that's what this picture right here is, right? So this is pure copper. Normally, because pure copper is all copper ions, the layers can easily slide past each other. But with brass, when we replace some of those copper ions with zinc, which is slightly larger, it causes the copper layers to not be able to slide past each other because they're not so uniformly made anymore. That zinc being in there makes the whole structure stronger because the layers can no longer slide past each other, giving brass that strength that copper is lacking. Aluminum is normally used for a lot of things in industry. And because it is so useful, lightweight, and conductive, it is used in airplanes, in construction, in making everyday objects. However, the main problem with aluminum is a very soft metal. And so when we try to make things out of it, it tends to not hold its shape. It tends to buckle very easily. So aluminum is usually doped with silicon and manganese to strengthen the aluminum and make engineering grade and industry grade aluminum. So most of the aluminum things that you use in everyday life or that you sit on or the airplanes that you fly on are not made out of pure aluminum. They're made out of aluminum alloys that have either silicon, manganese, or a combination of both in them. This is just to show you all the different types of aluminum. You don't need to know this. Don't try to memorize this. But you can see how there's a lot of aluminum alloys that have zinc and manganese. Some of them also use magnesiums, copper, and some other metals. But this is just all the different types of aluminum alloys. You don't need to know any specific aluminum alloys because there are hundreds of them that are used in industry. But you do need to know that most aluminum that we use in industry and in engineering is an aluminum alloy, usually with manganese or silicon added to them. Finally, bronze. Bronze is the other specific alloy that you need to learn about. Bronze is an alloy made of copper and tin. It is very strong and extremely malleable, which is why we use it for things like instruments and statues. So it's perfect for making things like art. The Statue of Liberty is made out of bronze, for example. The Colossus of Rhodes was made out of bronze. And bronze is also a substitutional alloy. Bronze is, if we look here, it's essentially copper with tin added to it in a substitutional manner where the different copper ions are replaced by tin ions, giving it its strength and malleability. The one alloy that we do not have here that you should probably know about is steel. Oops. Steel is an alloy of iron and carbon, and it is an interstitial alloy. Whenever we're asked for an interstitial alloy, this steel is usually the most common example, and the carbon in the steel usually makes the iron stronger, and it makes it less likely to rust. So it makes it stronger than iron, and it is less likely to rust. Which is why steel is such an important alloy in construction. But yeah, so now you know 3 different alloys, specific alloys, steel being the only interstitial one, and then brass and bronze being 2 substitutional alloys of copper, brass having copper and zinc, bronze having copper and tin. And you also know that aluminum is usually turned into an aluminum alloy whenever it is used in industry and engineering because it is a very soft metal. All right, let's move on from metals now and talk about covalent compounds. And covalent compounds are going to take a good amount of time because we got to cover a lot of different types of covalent compounds. All right. So let's talk about covalent compounds. Now, there are 2 different kinds of covalent compounds. There's simple molecular compounds and giant covalent compounds. We're going to talk about simple molecular first because these are the ones that we're most used to. Now, simple molecular compounds are essentially the kind of molecular or covalent compounds that we are used to. Things that are in molecules. Things like I2, carbon monoxide, carbon dioxide, methane, water. They form simple crystal lattices when they solidify. So whenever we freeze an ionic compound that's made out of molecules, like I2, like water, like carbon dioxide, we create a very simple molecular lattice. Ice is a very specific example of a simple molecular lattice where we have the molecules, which are water, at the points in the vertices. So a lattice that is molecular is made out of molecules at the vertices that are held in a specific arrangement. The distance between the molecules is longer than the distance between atoms in the same molecule. So, for example, in this water molecule, if we zoom in, the distance between the oxygen and the hydrogen is shorter than the distance between this oxygen and the hydrogen of a neighboring molecule. So this does not connect or bond the molecules together. What it does is that it connects them, or it attracts them through intermolecular forces in the solid. So the water molecule is still H2O, it's still two hydrogens and an oxygen, but they are attracted to other water molecules through, in the case of water, hydrogen bonding, but in generally speaking, for molecules, some kind of intermolecular force. The oxygen and the hydrogen are still bonded to each other with covalent bonds, but the molecules are connected to each other, attracted to each other through intermolecular forces. The whole idea of a simple molecular lattice is that they are held together by intermolecular forces and not bonds. Bonds are really hard to break. They hold the molecules together, the atoms in the molecule together, the oxygen to the hydrogen, but they are going to be very weak when it comes to separating the molecules from each other. So a simple molecular structure actually, how a simple molecular lattice actually has very low melting and boiling points, because what we're separating when we react them is the intermolecular forces, not the bonds that hold the molecule itself together. On the other hand, we have giant molecular structures, and these are new to us and very limited. Giant molecular structures, unlike simple molecular structures, are held completely together by covalent bonds. Giant molecular structures are covalently bonded compounds that do not fall into the simple molecular structure category. They have giant three-dimensional networks of covalent bonds throughout the whole structure. So something like these compounds tend to have very different properties from simple molecular compounds, because every single atom in that compound is covalently bonded to another. So the idea of intermolecular forces don't fit into giant molecular structures, because in giant molecular structures, every single atom is covalently bonded to another. The compounds tend to have very high melting and boiling points when compared to simple molecular structures, because when you boil or you melt an ionic giant molecular compound, you are breaking covalent bonds. Unlike when you melt or boil a simple molecular structure, you're breaking intermolecular forces. And that's where the difference comes in. These have really high melting and boiling points because you're breaking covalent bonds, because everything's covalent bonded to each other. Whereas in a simple molecular structure like water, when you melt it or boil it, you're breaking intermolecular forces that are holding the molecules together. And so their melting and boiling points are a lot lower. Some elements like carbon and like silicon can form a lot of different types of giant molecular structures. We call these different types allotropes. So an allotrope of an element are different crystalline or molecular forms of the same element. So allotropes are just different forms of one compound. For example, carbon can form diamond and graphite. Diamond and graphite are allotropes of carbon because they're different types of carbon. So we're going to look at some very specific giant molecular structures and allotropes of different compounds. So let's start by looking at different giant molecular structures, starting with graphite. Graphite is one of the allotropes of carbon, and it is the most common form of carbon. Now, graphite is very special when it comes to covalently bonded compounds because graphite can form or can conduct electricity, which most covalent compounds cannot do. Now, graphite can do that because of the structure. So let's discuss the structure first. Graphite is an allotrope carbon consisting of layers of carbon atoms that are trigonoplanar in structure and therefore are missing a bond. So whenever we have graphite, and I'm going to draw one layer of graphite to begin with, whenever we have graphite, what we have is a carbon atom with 3 bonds. Those 3 bonds go to other carbon atoms that themselves have 3 bonds. So on and so forth. So graphite is just a sequence of carbon atoms with 3 bonds each. Oh, that one's the wrong way. And so they form these trigonoplanar shapes. Because with 3 bonds, that means we have trigonoplanar central atoms. So we have all of these carbon atoms that are trigonoplanar. They form 3 bonds to other carbon atoms, and those repeat over and over and over again until we get this giant structure. That's why they're called giant molecular structures. So the carbon atoms form these hexagons with each other whenever they form graphite. But what you'll notice is that every one of these carbon atoms only has 3 bonds. Therefore, these carbon atoms are sp2 hybridized. By having sp2 hybridization, these carbon atoms all have a p orbital that is empty. So because they're all sp2 hybridized, because they're all trigonoplanar, they all have a sp2 hybridization and therefore a empty p orbital. Well, like we learned in the last chapter, whenever we have p orbitals that are not being used and they're next to each other, what they'll start to do is they'll start creating pi bonds by overlapping with each other. So all of these carbon atoms create these pi bonds with each other. But what's the issue? Well, these pi bonds are next to other pi bonds, and there's nothing preventing from those pi bonds to delocalizing all over this molecule. So going back to the picture, so what ends up happening is we get a gigantic pi bond all over the place. Going back to the picture we have here, we have all of these carbon atoms that are sp2 hybridized with p orbitals left over, and so all of those p orbitals form pi bonds with each other. Well, when they do so, they all merge together, causing what we call a delocalized pi orbital. So what you can imagine this as being is that we have all these carbon atoms with sigma bonds to each other, but each carbon atom only has 3 sigma bonds because of their sp2 hybridization. And because of sp2 hybridization, that p orbitals are left empty to delocalize all over the layer, creating these localized p orbitals. This is the hardest part to understand about graphite. Graphite is made out of layers of carbon atoms, so these carbon layers that we just talked about, where the carbons are sp2 hybridized in trigonoplanar shapes and have these p orbitals that delocalize. And so we have all of these layers of carbon with delocalized electrons above and below them. What happens because of that is that the layers of carbon are independent of each other, except for that they're held together by London dispersion forces. So we have these very strong layers of covalently bonded carbon with delocalized electrons held together to each other by intermolecular forces, which are very weak, by London dispersion forces, which are fairly weak. And this gives graphite a lot of different special properties. First of all, graphite has really high melting and boiling points. It requires a lot of energy to break the covalent bonds holding each layer of graphite together. And so, because it requires a lot of energy to break the covalent bonds between the carbons, Graphite, like all giant covalent structures, has really really high melting and boiling points. However, graphite is also very soft. It's very soft because the layers of graphite are only connected to each other by these very weak London dispersion forces. That's what these dashed lines are. These are London dispersion forces. So graphite, even though it's very strong, because the covalent bonds we see here need a lot of energy to be broken, graphite is also very soft because we can separate the layers of graphite from each other very easily. And so graphite kind of flakes off from itself. What we usually use graphite, what we see graphite in, is pencil lead. If we have a pencil, the lead in that pencil is graphite. So how do pencils work? Why can we write with pencils? We can see this graphite here in the tip of the pencil as being these layers of graphite. When we rub the pencil against a piece of paper and we create friction, these intermolecular forces that are holding one layer to each other break, leaving behind a layer of graphite on the piece of paper that we're writing on. And then another one breaks as you keep dragging the pencil across the paper. Another layer breaks because the London dispersion forces are really weak and they can be broken by friction. And so we keep leaving layer after layer of graphite on the paper due to these London dispersion forces being so weak. And that's how we write with a pencil. What we see as writing are just layers of graphite being left behind due to those weak London dispersion forces holding one layer to another being broken. Finally, graphite is one of the very few, if not one of the only, covalently bonded compounds that is a good conductor of electricity. Now, like we said, metals can conduct electricity because of the delocalized electrons. But most covalent compounds, even when solid, cannot conduct electricity, or even when melted or gases, because they lack mobile charged particles, which is what we said earlier we needed to conduct electricity. Mobile charged particles. Now, usually, covalently bonded compounds don't have mobile charged particles because all of their electrons are bound in sigma bonds or very, very limited pi bonds. But graphite can conduct electricity thanks to this sea of electrons we talked about earlier, these delocalized electrons. Because graphite, I put it the wrong way. Because graphite has this area of delocalized electrons because of those p orbitals that are merged together into this delocalized pi orbital all over the layers of graphite actually conduct electricity because those delocalized pi orbitals are mobile electrons. Let me double color this. They're mobile electrons, meaning that they're mobile charged particles. So thanks to that delocalized area of pi bonding of electrons in graphite, graphite is one of the very few covalently bonded compounds or covalently bonded things that can conduct electricity. So a pencil could be used as an electrical conductor. Lead, or what we call lead, which is actually graphite, could be used as an electrical conductor. So this is an example of, or the details that you need to know about graphite. Let's look at an allotrope of graphite, because graphite is an allotrope of carbon. It is a giant covalent structure that is completely made out of carbon. So, because graphite is an allotrope of carbon, that does dictate that there should be another allotrope. And that other allotrope is diamond. Diamond is an allotrope of carbon where the carbons are sp3 hybridized instead of sp2 hybridized, like in graphite. So with diamond, the carbons are sp3 hybridized because they have this tetrahedral shape. Every carbon atom in diamond, sorry, not graphite, diamond. Every carbon atom in diamond has 4 other carbon atoms bonded to it through this tetrahedral conformation, making every single carbon atom into a tetrahedral with sp3 hybridization. The network of covalent bonds is carried out in all directions to form this structure throughout the diamond. This structure is what gives diamond its hardness. So let's talk about the properties of diamond. Diamond has really high melting and boiling points, like all giant covalent structures. They have high melting and boiling points because it takes a lot of energy to break all these covalent bonds when we are melting or boiling diamond. Unlike simple molecular compounds, which are held together by intermolecular forces, diamond is held together by covalent bonding. That covalent bonding requires a lot of energy to break, and so it gives diamond very high melting and boiling points. Now let's talk about diamond's main property, which is its hardness. Diamond is the hardest naturally occurring substance on planet Earth. Diamond is so hard that the only way you can scratch diamond is with another diamond. The reason why diamond is so hard is because of this covalent structure. Whenever diamond is put under pressure or force, so if I hit the diamond with, again, I'll draw my little hammer. So if I hit my diamond with a hammer, that force that I'm hitting the diamond with, that I missed here, that force that I'm hitting the carbon with is spread out throughout the diamond through those covalent bonds. So that force that I hit the diamond with, because of its shape, instead of all going to a single carbon or 2 covalent bonds, that force is spread out and goes through the whole diamond molecule through a covalent bonding. Not only that, those covalent bonds are really strong, and so this makes diamond extremely hard. It is hard to scratch because of the omnidirectionality, which is what we call it when there's bonds in every direction, of the covalent bond lattice and its tetrahedral structure. Finally, diamond does not conduct electricity. Unlike graphite, which has the localized pi orbitals and the localized electrons, diamond's carbons are sp3 hybridized, meaning that there are no p orbitals left over. Because there are no p orbitals left over, diamond does not form a delocalized area of electrons, and therefore it cannot conduct electricity like graphite can. So even though both diamond and graphite are made out of carbon, they are very different materials. And this is all due to how they're created. The process of creating graphite is very quick, very easy, whereas diamond needs a lot of temperature, a lot of pressure to create the structure that we see here. So diamond and graphite are other allotropes, are 2 allotropes of carbon with very different properties. The other and the last giant covalent structure that we're going to look at is silicon 4 oxide, or what we know as silicon dioxide. Now, silicon dioxide is a compound, unlike diamond and graphite, which are allotropes of a single element. Silicon dioxide is a giant covalent structure made out of a compound, a silicon and oxygen compound. Silicon dioxide, or silicon 4 oxide, has many forms, but the one found normally in nature, in things like quartz and sand, has a tetrahedral structure very similar to that of diamond. The only difference between the structure of silicon dioxide and diamond is that instead of having just all tetrahedrals, we have tetrahedrals that are connected through a oxygen bridge. So each silicon has an sp3 hybridization and creates a tetrahedral structure to an oxygen. Those oxygens then bridge the connection between the silicons, creating an expanded tetrahedral structure we see here. So if we look at this structure right here, we have a silicon atom in the center that is sp3 hybridized. So this silicon is let me set it for color. This silicon is sp3 hybridized. That silicon therefore creates a tetrahedral But those tetrahedrals, instead of going to other silicons like in diamond, they are going to oxygens, which we see here. That oxygen is then in a bent structure, which we can't really see here because we're looking at it from a different side. But that bridges the connection between two other silicons, which are both sp3 hybridized. And then that silicon will have a tetrahedral structure connecting to other oxygens, so on and so forth. So we get this expanded tetrahedral. So you can see a tetrahedral here that the silicon forms, but it is expanded by oxygen bridges. You can see here as well, where you have this tetrahedral silicon, two oxygens, and then the oxygen bridges the connection to another silicon. So because of that, the properties of silicon dioxide and diamond are very similar, but the main difference being that all of the properties of diamond are present in silicon dioxide at a lower extent. Because each oxygen is also sp3 hybridized and creates a bond to silicons creating those bridges, the structure itself is a little weaker because of the extra space created by the oxygens. Silicon 4 oxide has similar properties to the diamond, but they're less extreme. So it still has a higher melting point and boiling point, but not as high as diamond. It is still hard. Quartz are very hard, but not as hard as diamond. They cannot conduct electricity just like diamond. Now, why do we say the oxygens are sp3 hybridized? Remember, these oxygens have lone pairs of electrons on them. And that creates 4 connections or 4 attachments in the oxygens, making them also sp3 hybridized, just like the silicon was sp3 hybridized. So silicon dioxide, very similar to diamond, but weaker properties because of that extended tetrahedral created by the oxygen bridges. It is important to say something that you might not think about, but you might be asked about in the Cambridge exam, which is that silicon dioxide has this shape. Silicon, pure silicon, is extremely similar to diamond because they're both group 14 elements. Silicon also forms the same tetrahedral structure that diamond does, that the carbon in diamond does. The only difference is that silicon is bigger, so the properties of silicon are weaker. So if you're ever asked about the properties of silicon, know that you are essentially going to draw the same thing you draw for diamond, but because of the size of the silicon versus the atom of carbon, you're going to have weaker properties. So silicon is also hard, just not as hard as diamond. Silicon is also high melting point and boiling point, just not as high as diamond. And then with silicon dioxide, not the element but the compound, that structure of silicon that is tetrahedral is expanded by the oxygens, creating a much larger tetrahedral and therefore weaker. That is it for this section of chapter 5. We will look at the last section in the next video, which looks at other allotropes of carbon we have not discussed here because they're not giant covalent structures.